Hey guys, this is the next Calc 3 video. It's 10.3, which is vectors in the plane and in space. So first we need to learn how to represent vectors algebraically. And I taught you about the initial point and the terminal point in a previous video. And those points be represented, or the terminal point would be represented as v1, v2. And the position vector is notated as you can see by my horrible computer handwriting. Vector v equals component v1 and component v2 in like triangular brackets. The same can be said in space, where there will be additional components, where components are like v1, v2, v3, v4, blah blah blah, vn, where n is an infinite number. And if a vector does not originate at the origin, then the notation for that vector can be is shown here. Vector v equals v1 minus whatever that corresponding point would be for its initial point, v2, and then same thing minus where the initial point is for that corresponding spot. And the same can be said for space. You just keep going until eventually you hit whatever number you got. An equality for vectors is only true if, and only if, that's what this means. Like component 1 of v is the same as component 1 of w, component 2 of v is the same as component 2 of w, and it keeps going for however many you have. And here's your operations of vectors. Vector v plus vector w is component v, or component v1 plus component w1, comma, component v2 plus component w2, vector v minus vector w, which technically this isn't real, vector v1 minus, not vector v1, component v1 minus component w1, component v2 minus component w2, scalar multiplication, av1, av2, and the same can be said for space, just add more components. And this I wrote out because I was not about to type all of this. So I'm sorry, you'll have to deal with my handwriting for a moment. Vector u plus vector v is the same as vector v plus vector u because it's commutative. Vector u plus open parentheses vector v plus vector w close parentheses equals open parentheses vector u plus vector v close parentheses plus vector w because it's associative. Vector v plus vector 0 plus vector 0 plus or equals vector 0 plus vector v equals vector v because that's the identity or additive identity. Vector v plus vector v in the opposite direction equals vector 0 because that's the additive inverse, and I moved that without meaning to. Scalar a times open parentheses vector u plus vector v close parentheses equals a times vector u plus a times vector v because that's the distributive scalar multiplication stuff. And scalar a times open parentheses scalar b times vector v close parentheses equals open parentheses scalar a times scalar b close parentheses times vector v is the linearity property. And scalar 1 times vector v equals vector v because that's the scalar multiplication identity. Okay, so parallel vectors. If vector w or vector v is a scalar multiple of the other, then they are parallel vectors. So 3 divided by 3 is 1, 6 divided by 3 is 2, 9 divided by 3 is 3. your A is 1/3. These are parallel. But say the 6 became a 4. Then they are not parallel because 3 divided by 3 is 1. 4 divided by 3 is not 2. But 9 divided by 3 is 3. So they're not parallel. Easy enough, right? So your magnitude of vectors. Magnitude of a vector is also referred to as its length or norm, and it's denoted as, I call this the absolute value. It just gets rid of direction, which means it gets rid of the negative sign, of vector v. The magnitude of vector v is the distance between the vector's initial and terminal points. Therefore, the vector can be computed with the distance formula, which we should all know by now because we've covered it. But v1 squared plus v2 squared plus blah 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 vn squared. Square root of all that, by the way. Okay, magnitudes of vectors. The magnitude of a vector is a scalar quantity. Magnitude of a scalar multiple can be noted as, so if you have the magnitude, there's supposed to be another line here, I cut it off, of scalar A times vector V equals the absolute value of A times the absolute value of vector B. Same but different, you know. Now you have unit vectors. And a unit vector is a vector of magnitude 1. For any non-zero vector, you can derive a unit vector with the same direction as a non-zero vector using this formula, which is vector u equals vector v divided by the magnitude of vector v, which makes sense because you're just trying to get rid of its length, or make the length 1, so you just divide by its length. You know, that way it's 1. Makes sense. Finding a vector's corresponding unit vector is called normalizing the vector. Maybe because the magnitude is also called the norm, and this could be because mathematicians wanted to sound fancy, or it's because magnitudalizing just sounds ugly. So your standard basis vectors are I, j, or I hat, j hat, k hat, and this is what they hold. And these vectors are located along your axes. I is with x, j is with y, and k was with z. To write a vector in standard basis notation, multiply the vectors along the axes, or the vector's components, this should say components, along the axes. Ooh. Yeah, we're just going to ignore what that says for a minute. You just multiply components by your standard basis vectors. That's all you do. Ignore everything that says. I'm tired. So finding a vector from direction magnitude. Say your friend Amy says that she has an angle and a magnitude of a vector, but she does not have the vector itself. You can tell her she is absolutely incorrect thanks to this formula. Vector v equals the magnitude of vector v times cosine theta I plus sine theta j. Easy peasy. Take that, Amy, learn some math. And if your name's Amy, I apologize. Please read your name as Johan. And that's it, guys. It's been fun.